Welcome to the video lecture that will review graphing, intercepts, and symmetry. So today we're going to talk about some of the basic things that you need to know about graphing, and we're going to start by just kind of reviewing some of the more common graphs that you should know how to graph by hand. So first of all, the definition of a graph of an equation or an inequality is the set of all points x, y that make that equation or inequality true. So there's some common types of graphs that you definitely need to be able to sketch by hand, and the most basic one of all, of course, is the line. So y equals 3x minus 2. We know that that's a line because it has x to the first and y to the first, so we know that it's going to have the shape of a line. And there's lots and lots of ways to graph lines, but since this line is in the form y equals mx plus b, I'm going to show you the slope-intercept method. What this tells us is that that coefficient of x, which in this case is this 3, that's your slope. So 3, and the constant on the end, that's your b, and b stands for your y-intercept. So we have a y-intercept at -2. So when you use this slope-intercept method, you always plot the y-intercept first as your starting point. So you're going to go to your y-axis, and you're going to put a dot at -2 on that y-axis. So the line passes through that point. Now to get a second point for our line, because every line needs 2 points, we're going to use our slope. And in this case, our slope is 3, but in this problem, I tend to encourage students to rewrite it as 3 over 1, because 3 over 1 is going to be thought of as our rise over our run. So when I rise 3, since it's a positive 3, I'm going to rise up 3, so 1, 2, 3, and I'm going to run to the right 1 because it's positive. So I'm going to go up 3, over 1 to the right, and there's my second dot. Now notice I did that rise and run from my y-intercept. So up 3 over 1, connect my 2 dots, and there's my line. Okay? So everyone should know how to graph a line by hand. The next equation is a little step higher, or a little more difficult, because now it has an x squared. And you want to know that whenever there's an x squared, that is going to be a parabola. So this is the graph of a parabola. And there's lots of things that you should know about parabolas at this point, coming from an intermediate algebra class. And you should know the basic shape of just y equals x squared. Y equals x squared is just a parabola that's a U shape pointing up, and it has a vertex at the origin, and then it has a certain pattern to it to get some side points. The side points come from graphing that vertex first, and then going over 1, up 1, and there's 2 more side points, and then the pattern continues, but this time you go over 1, up 3 to get 2 more side points, and if you needed to continue, it would go over 1, up 5, over 1, up 7, and so forth. So this is how we're going to get our graph. But before I can even use my pattern, I need to know what my vertex is. And the vertex, normally on y equals x squared, is at 0, 0. But this time we have a -4 on the side. So what kind of a shift is it when you subtract 4 off to the side of your graph? This is a shift down. It's a vertical shift because it's off to the side of that x squared. And because it's a -4, we're going to go down. So instead of starting at 0, 0, we're going to start at 0, -4. So we're going to go from the origin, and we're going to go down 4 units, and now the vertex has been shifted down to that point. So that's going to be our starting point. That's our vertex. That's this middle point right here. And then if you know that vertex and you know your pattern, you can get some more side points. We're going to go over 1, up 1 to the right, over 1, up 1 to the left. And then over 1, up 3, 1, 2, 3 to the right, and over 1, up 3 to the left. So here, when I connect them with a nice rounded U shape, is my parabola. So it's good to know this basic pattern for a parabola and to know some of your basic shifts up, down, left, and right. And we'll review that as the course progresses. Okay, let's take a look at a square root graph. This is a basic graph that you want to know the shape of as well. Now, if you don't have it memorized or you've forgotten, you can always make a table of values. So I'll do that for this first example. but from this point on you really do want to memorize the pattern. Because this is a square root of x, the x's that you plug in have to be 0 or positives, because when we're graphing, we're not allowed to graph imaginary numbers. And if you put a negative under a radical, that makes it imaginary. So the first or smallest x that you could possibly use for an input here would be 0, since negatives won't work, and square root of 0 stays 0. Then I could use x equals 1, and square root of 1 stays 1. And I probably wouldn't want to use 2, because square root of 2 is going to give me a yucky decimal, which I can't really plot very well. So the next best choice for x would be the next perfect square. So 1 squared was 1, 2 squared is 4, so if I use 4 for x, then the square root of 4 turns out nicely and I just get 2. So you want to make sure that you're using nice perfect squares for your x so that you get nice y values back. Otherwise you'll be dealing with decimals. So 3 points is good enough. Let's go ahead and plot these. 0, 0 is at the origin, then 1, 1, and then we're going to go over 4, 2. And a square root graph always starts at the origin and arcs slowly up to the right. And that is our typical square root shape before you shift it or flip it or do anything crazy like that. Now what's the pattern involved here? If you want to memorize this, you plot that initial point first, which is always going to start at the origin unless you shift it around. And once you have that starting point, you always go up 1 over 1 to the right, and then up 1 over 3 to the right. So it's exactly like the pattern for the parabola, except it's doing that shift 1 and 3 horizontally, whereas for the parabola we went 1 and 3 vertically. Okay? So very similar pattern, but the square root goes horizontally to the right. Okay, let's try another common graph that you need to know, and that would be the absolute value graph. So that's these vertical bars right here. And what you want to remember about an absolute value is that it always has a V shape. It looks like a great big V. And what you want to remember is that if it's a V shape, it's got to have a vertex. And how do you find where that vertex is? Well, normally, absolute value of x has its vertex right at the origin, but this time we have a +2 inside of our absolute values. So what does a +2 do to our graph? If you remember our example up above here, this -4 shifted you down 4, and it was outside of this square. It was away from that x value. Now that's a different kind of shift than what's going on down here, because this time the +2 is inside, next to that x, inside of those absolute values. So instead of shifting up and down, this is going to shift left or right. And it's kind of backwards from what you would expect. When you see a +2, you actually shift left 2. Normally you think +2 goes to the right, but in this case for horizontal shifts, they go in the opposite direction. So this is going to be a shift left 2. Now another way that you could figure that out is just to take whatever you see inside of this absolute value and find out when would it be 0. When is that going to hit 0? And if you solve that, you would get x equals -2, which means that on my graph, when x equals -2, the y value is going to be 0, and that's going to be my vertex. And you'll notice that if normally the vertex is at 0, 0, what have I done? I've shifted left 2 units. Okay? So a couple ways to think about it. Either find where this inside stuff is 0, and that's where your x value of your vertex is, or else shift, think of this as a shift left 2 because we had a +2 on the inside. Now that we know our vertex, we want to know our pattern. And this is a V shape. So the pattern for your vertex, or for your absolute value, is over 1, up 1 to the right, over 1, up 1 to the left, over 1, up 1 to the right, over 1, up 1 to the left, and so on. It just goes over 1, up 1, over 1, up 1, over 1, up 1. So you get these nice straight lines to the right and to the left. And that's what makes it that nice V shape. So there's no curving at all. It's just straight lines. So this has a consistent pattern of over 1, up 1, over 1, up 1 each time. Okay? So you want to be able to graph any kind of a line a parabola, a square root, and an absolute value. Now let's take a look at this next example. When you see this, you see x squareds and y squareds both. So that should trigger for you the thought that this is probably a circle, and you know that it should be because it's x squared plus a y squared. This has to be plus, and the coefficients in front of those x squareds and y squareds are equal. So this is the graph of a circle. Now, to graph a circle, the key important parts of a circle are its center and its radius. And the standard form for a circle, if you remember this at all, would be something like this: x minus h quantity squared plus y minus k quantity squared equals r squared. If we had our circle in this form, then the center would be at h comma k, and the radius would just be r, the square root of this constant on the right-hand side. Unfortunately, our equation doesn't look like that. We don't have any parentheses involved. So what we're going to have to do here is transform this given equation into this sort of factored form. So the first thing I'm going to do is I'm going to rearrange these terms a little bit. I'm going to put my two x terms together, x squared minus 2x, and I'm going to leave a little space. And then I'm going to put my two y terms together, my y squared and my 2y, and I'm going to leave my constant 2 on the right-hand side. And what we're going to need to do to take this x squared minus 2x and turn it into x minus something squared is the process called completing the square. Usually students hate to do this, but it's fairly simple to do once you get the hang of it. All you want to do is, first of all, make sure that the coefficient in front of the x squared and the y squared are both 1s. And in this case, they already are. If they weren't, you would need to divide every single term by that coefficient to get rid of it. So once this leading coefficient is a 1, then you can easily factor this by taking 1/2 of this middle coefficient. So 1/2 of negative 2 is minus 1. That's why I want a minus 1 right here. Now think about that for a minute. If I were to FOIL this out and distribute this out, I would get x squared, I'd get a minus x and another minus x, so I'd also get a minus 2x in the middle, but I'd also get a plus 1 on the side, which I don't have up here. So I need to have a plus 1 in order for these three terms to factor into the quantity x minus 1 squared. However, I can't just add a 1. That changes the problem. So to balance it out, I'm going to add a 1 to the other side as well, so that I'm doing the same thing to both sides to keep the equation balanced. So now we've rewritten the x's in this factored form. So let's try that again for the y's. So we're going to add to this y squared minus 2y, and we're going to need to change this into y minus something squared. So to figure out what goes right here, you always take 1/2 of this middle coefficient, assuming you have a coefficient of 1 up front, which we do. Half of negative 2 is negative 1, so I want a minus 1 in the middle. And if I were to FOIL this out, I'd get the y squared back, I'd get the minus 2y back, but I'd also get a plus 1. So these three terms factor into that. But since I didn't have the plus 1 in the original problem, I've got to add it to the other side as well to keep the equation balanced. So now these truly are equal statements on the left and the right side. So the left side now looks like this factored form, but I have a new constant on the right side. 2 plus 1 becomes 4. So this is good news, because now that I have it in this nice form, I can easily tell what the center is. The center will be these numbers that I see, and notice it's the opposite sign of what's inside. So if I see a negative 1 next to that x, my center is actually going to be at positive 1. And if I see a negative 1 for y, my y value is going to be positive 1. And my radius is the square root of the constant on the right-hand side. Square root of 4 becomes 2. So now that we know our center and our radius, we should be able to plot our circle. So here's how I do it. I locate that center first, so 1, 1 would be right here. That's technically not on the circle itself, but we need it as a reference point. From there, I need a radius of 2. So I'm going to go right 2, up 2, left 2, and down 2 from that center, and through those 4 points I'm just going to draw as best a circle as I can. I don't have a lot of accuracy with my pen on my computer here, but you can imagine that as being a slightly more circular shape. Okay, use your imagination. So there's my graph. Okay? All right, let's try another example. Now this one has kind of some funny notation. It's called set builder notation, and this basically is just a funny way of saying the set of all x comma y's, so all points x comma y's, such that, that's what this vertical bar means right here, that means such that y is greater than or equal to 0. So we want to plot all the points, all the ordered pairs, that have a y value that's greater than or equal to 0. So think about that for a moment. What would it look like for y to equal to 0? What does the graph of y equals to 0 look like? What are all the points that have y being equal to 0? Well, y equals to 0, you should know that that's a horizontal line. That's just the x-axis. So all the points on the x-axis have a y value that's 0. So there's y equals to 0. What would it then mean if I want y greater than or equal to 0? When it's equal to 0, that's the line itself. Which points are going to have y's greater than 0? Well, greater than 0 y's are all these y's going up, because these are positive y values. So in this graph, it's actually going to be shaded in, because all of these points going up above that x-axis, or that y-axis, excuse me, the x-axis, have y values that are either positive when they're above or equal to 0 when they're actually on that x-axis. So this is graphing an inequality, and whenever you're graphing an inequality, it usually looks like some kind of curve or line as your boundary, and then you shade either above or below it. So my final answer would actually be this shaded in picture. All right, here's another one. This time we want the set of all points x comma y such that the absolute value of x is less than 3 and the absolute value of y is greater than 2. So let's start with absolute value of x less than 3. Absolute value means the distance away from 0 on a number line. So this is asking for all the points x comma y that have a distance away from 0 that's less than 3. Now, this is something that you learn in intermediate algebra when we talk about absolute value inequalities. And if you think about this for a moment, the only x values that have a distance less than 3 would be all the x's in between -3 and +3, because their distance away from 0 would be smaller than 3. So that's what absolute value less than 3 turns into. Now if we change this inequality to a greater than for the y's, now we want the distance to be greater than 2. So up here, if you need to visualize this, we could go 3 to the right or 3 to the left. So that's what we're talking about right here. This interval is all these x's. For y's greater than 2, this time we want our distance to be larger than 2. So that would have to be points over here to the right or points over here to the left. So this corresponds to all the y's bigger than 2, which is the right side, or all the y's less than -2, which would be to the left side. Now that's one-dimensionally thinking. We need to think in terms of 2 dimensions, x's and y's. So what would it mean for all the points that have x's between -3 and 3? Well, what does it mean for x to equal 3? On a 2-dimensional graph, you got to know that that's a vertical line. So x equals 3 would be something like this. Now notice I'm using a dashed line, not a solid line, because we don't actually get to include the line itself since there's no equal bar. We want x to be strictly less than 3. What would x equals -3 look like? Well, that's also a vertical line, but it would be on this side of the origin. So if we want all the x's between -3 and 3, then that means we're talking about this shaded region right here. So two-dimensionally, those would be all the points that have an x-coordinate that's smaller than 3 in absolute value. All right, now we're going to do it for y's. So think about what y equals to 2 would look like two-dimensionally. That's a horizontal line because it's y equals a constant. So y equals 2, and again I'm going to use a dashed line, would be like that, because I want to be strictly greater than 2. So which way would be greater than 2? Going up or going down? Well, if 2 is right here, going up would have x's that are bigger than 2. So I want to go greater than, so I'm going to go this way. So that took care of that piece. Now let's look at the other piece. We want y equal to -2, which is also horizontal, another dashed line. But this time we want all the y's to be less than -2. So here's -2. Which direction would be less than -2, going up or going down? Well, these y's are below -2, so this is less than going down. So I would shade down. Okay, let's finish it off. There's a key word here that we've overlooked, and that's the word and. And in mathematics means intersection. So we want for our final answer the intersection of the red shaded region with the blue shaded region. So what points are both in the red region and the blue region at the same time? It would be this part of the stripe and this part of the stripe. Below -2 and above +2, but between -3 and 3. So your final answer would look like this green shaded region. Okay? All right, let's try another inequality. This time we have x squared plus y squared less than or equal to 1. Now ignore the inequality for a moment and just think about the equation itself. Let's just think about how would you graph x squared plus y squared equals to 1. This should look kind of familiar to what we talked about earlier up here. This is an equation that has an x squared and a y squared with a sum, and the coefficients of the x squared and y squared are both 1. That makes it a circle. So this is a circle. It doesn't have any h or k being subtracted off to the side, so that means its center is just 0, 0. And the square root of this constant on the right-hand side, square root of 1, stays 1. So this is just a circle with a center at the origin and a radius of 1. So let's draw that. Here's the center. I'm going to go 1 to the right, 1 up, 1 left, 1 down. Connect the dots with a circle. There's my boundary. Now I drew it nice and solid instead of dashed because I have an equal bar, which means I want to include the actual boundary curve in my solution. Now because it's an inequality, whenever you see inequalities for graphing problems, you do have to have some shading. So we need to figure out which way to shade. And in this case, there's only 2 ways you could shade. You could either shade inside the circle or you could shade outside the circle, and we need to know which way to shade. And the way to figure that out is to use what's called a test point. Now the test point can be anything so long as it's not on the boundary curve itself. And a really good test point to use that usually always works is the origin, 0, 0. Because in this case that center point isn't technically on the rim of the circle, so I can use it as my test point. So all you have to do to test it is substitute in 0 for x and 0 for y, so 0 squared plus 0 squared, and see if it makes this inequality true or false. Well, 0 squared plus 0 squared stays 0. Is 0 less than or equal to 1? Yes, so that's true, which means it works, which means you want to include the origin in your solution. And since the origin was inside the circle and it worked, then all the points inside the circle must also work. So this solution is just the filled in circle. Okay, on the next page here, we're going to talk about some important characteristics of a graph that are important to look at when you're trying to graph things, and important things to look for because they give you lots of important information about your curve and about your graph. One really key thing to know is intercepts. So let's review how to find an x-intercept. An x-intercept is going to be the places where a curve intersects the x-axis. So your x-intercepts here would be right here, 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 and here. And what do all of these points have in common? They all have a y value equal to 0. So to find an x-intercept, you let y equal to 0, and you're just going to solve for x. That would be the algebraic way to figure it out. And we'll practice this in a moment. Now a y-intercept is going to be wherever your graph crosses or intersects the y-axis. So in this case, that would be this point right here. And in that point, you'll notice that the x-coordinate is 0. So to find a y-intercept, you're going to let x be 0, and you're going to solve for y. Okay? So they're kind of opposites. To find an x-intercept, you let y be 0. To find a y-intercept, you let x be 0. Alright, so those are the definitions. We'll come back and use this in just a moment, but let's take a look at some symmetry tasks next. Now there's 3 major types of symmetry that you need to be able to explore. And the first type of symmetry is called symmetry with respect to the x-axis. So let me draw a picture of something that would be symmetric with respect to the x-axis. Something like a sideways parabola, something like this. Now what makes this symmetric with respect to the x-axis is that if you were to fold it over this x-axis, you would get the same image on both sides. And another way of thinking of that is that they share these 2 points on your curve. So this is just a random point x comma y. Then this point down here would have to be its sort of reflection over that x-axis. So notice it would share the same x-coordinate. Those would have to match. But the y values would not be the same. They would be the same value or magnitude, but they would be opposite signs. So this would be the same as the y up above, but it would be its opposite because you're going down instead of up. So that fact right there is how we determine our test for symmetry. So to figure out if something is symmetric with respect to the x-axis, what you're going to do is you're going to replace the y in your equation with minus y. And you should get back an unchanged equation. If the equation remains unchanged, then that means you are symmetric with respect to the x-axis. So replace y with minus y, and the equation should be unchanged. Now notice in my example here that this picture that I just drew would not be a function, because I could easily draw a vertical line right through those 2 points, and that vertical line is intersecting my graph in 2 points, which means it doesn't pass the vertical line test. So anything that is symmetric with respect to the x-axis is not a function, because it will fail the vertical line test. So you don't see a whole lot of symmetry with respect to the x-axis in mathematics, because a lot of mathematics only deals with functions. Okay, let's take a look at another common type of symmetry, symmetry with respect to the x-axis, or excuse me, the y-axis. So let's draw a picture of that. That would be just your typical y equals x squared, something like a normal parabola, something like this. And what makes it symmetric is that if you have a random point over here, x comma y, then you would have its image reflection over on this side of that y-axis. And what's the relationship here? They both are at the same height, so they both share the same y, but the x's would be opposites. So this time the test is going to be replace the x value with its opposite, and the equation should be unchanged. If that's true, then that means you do have symmetry with respect to the y-axis. Okay? One more type of symmetry that's very common is called symmetry with respect to the origin. So this would be the type of symmetry that you might see with like an x cubed graph, something like this, where if you were to take this curve or this point, x comma y, and rotate it 180 degrees around the origin, so turning this and rotating it around, you would get the same point over here. Now on this side it was over x and up y, and you can see that we're taking this point, and when we rotate it now in my example here, it's moving from the first quadrant down to the third quadrant. So that would now have a negative x for the x value and a negative y for the y value. So the coordinates of this point would be negative x, negative y. And that's how we get our test. If you're going to have symmetry with respect to the origin, then this time you're going to replace both with their opposite. So you're going to replace x with minus x and y with minus y. And if you do that and you get back the original equation so that the equation is unchanged, then that means you do have symmetry with respect to the origin. And we're going to practice this in just a moment. Now one last comment before we move on, and we'll get to this in future video lectures as well, but whenever you talk about something having symmetry with respect to the x-axis, there is another name for that. That would be called a function that is even. And you can kind of see from my example here, this was an x squared. It had an even power to it. So typically equations or functions that have even powers throughout would have this type of symmetry, symmetry with respect to the y-axis. My example down here was of an x cubed, which had an odd power, and for most functions that have all odd powers, they would also have this symmetry with respect to the origin. So another name for this kind of symmetry would be odd. We would say a function is odd if it has symmetry with respect to the origin. So just a couple of more vocabulary words to know. Alright, let's practice what we just talked about. So we're going to be given an equation, some kind of curve, and we want to find its intercepts, and we also want to determine what kind of symmetry it has. So let's start with our intercepts first. So to find an x-intercept, you let y be 0. So we would substitute in a 0 right here where y is. So this would give me 0 equals x cubed minus 6x. Now this is a higher powered function, x cubed. So the only way we're going to be able to solve this by hand is if it factors somehow. And luckily enough for us, it does, because I can pull out a GCF of an x, and that leaves me with x squared minus 6. So when does each of these factors equal 0? Well, this one's going to equal 0 at 0, and x squared minus 6 equals 0. If I add that 6 to the other side, take a square root, don't forget your plus or minus. So I have x-intercepts at 0 and at plus or minus square root of 6. So there's actually 3 intercepts here. Alright, so that's for your x-intercepts. Let's find your y-intercept. So to find your y-intercept, you're going to let x equal 0. And this is usually a lot easier to figure out, because all we have to do is plug in 0 for this x and 0 for this x, and you can see that that's going to make both of these x terms cancel out, so we're just going to get y equals 0. So my x-intercepts are 0, 0, and plus or minus root 6 comma 0. Notice the y values were both 0 there. And my y-intercept was also 0, 0. So the origin is both an x and a y-intercept. Okay, so we know our intercepts. Now let's determine our symmetry. So to figure out your symmetry, you need to apply all 3 tests and determine whether or not they're true or not. So let's start with x-axis symmetry. And the test for that is to replace the y with the opposite of y. So if you want x-axis symmetry, it's the y that you're changing. So what do I mean by replace y with minus y? You go to your equation over here, and you see wherever that y is, you're going to change it and substitute in a minus y instead. So this left side becomes minus y. I'm not doing anything to the x's, So I'm going to leave those the same. And now you want to solve this for y and compare it back with the original equation. So to solve this for y would require dividing through every term by that negative, which makes this become positive y. X cubed divided by negative 1 is negative x cubed, and a negative 6 over a negative 1 becomes a positive 6x. Is this the same equation as what we started with? No, because the signs are backwards. So this doesn't work, which means we do not have x-axis symmetry. Okay, let's try it again. This time we're going to try y-axis symmetry. So if you want y-axis symmetry, it's the x's that you change. So we're going to take x and we're going to replace it with minus x. So this time we're not doing anything to the y. Y is going to stay y, but the x's become minus x's. And when you're substituting in these minus x's, you need to use parentheses. So I'm going to replace this x with a minus x in parentheses, and I need to cube that whole thing. And then I'm going to change that x next to the 6 also to a minus x using parentheses. And now you want to simplify this on the right-hand side. Now what happens to a negative when you cube it? Because that's an odd power, it stays put. So you can take that negative, it's going to stay there, and you can remove those parentheses, but now there is still a negative out front. Then a minus 6 times a minus x becomes a positive 6x. Is this equation the same as the original? No, because the signs are opposite again. So it does not have y-axis symmetry. So the last test is for origin symmetry. So this time we're going to replace x and y with their opposites. So this y becomes a minus y, and these x's become minus x's wrapped in parentheses. So I'm going to leave the minus y there for a moment while I simplify the right-hand side. Just like we did before, we can lose these parentheses around the cube, but the negative will stay out front. And I just get negative x cubed, and a minus become plus 6x. But can't quite compare these two yet because I haven't solved for y. So now I would want to divide every term by a negative 1. So this becomes positive y equals positive x cubed and a minus 6x. Is that equation the same as the original? Yes. So that means we have origin symmetry. And in other words, this is an odd function. And we could have predicted that because we had odd powers, an x cubed and an x to the first. Okay? So it's a little tedious, but that's what you're going to need to do to show algebraically that you do have origin symmetry. All right, let's try another example. So x equals absolute value of y. Let's find the intercepts first. So to find the x-intercept, you're going to let y be 0. So if I plug in a 0 on this side, I'm just going to get x equals absolute value of 0, which is just x equals 0. So 0, 0 would be that x-intercept. Likewise, for the y-intercept, you're going to let x be 0. So now I put a 0 on the left side. 0 equals absolute value of y. The only way that's true is if y itself is 0. So again, that origin is both an x and a y-intercept. Alright, now let's do our symmetries. Symmetry tests. So if I want to test x-axis symmetry, I'm going to replace y with minus y. So leave x alone on the left side and change this y with a minus y. Because we have absolute value bars, what does that absolute value do to the negative? The absolute value of negative y is exactly the same thing as the absolute value of positive y. That absolute value strips away that negative because it's not going to affect the answer since absolute values make everything positive. So if I remove that negative because it gets absorbed by that absolute value, is this equation the same as the original? Yes. So far we've got x-axis symmetry. Let's check the others. Let's try y-axis symmetry. So for y-axis symmetry, now you're going to change the x with its opposite. So the x on this side becomes a minus x. And the question then would be minus x equals absolute value of y. to make it comparable to the original, the original was solved for x. So let's finish solving this for x as well by dividing through by our negative. So this becomes x equals an absolute value of y divided by -1. That's just going to move that negative up in front of that absolute value. I'm just moving it up to the top. Is that the same as the original? No. So we do not have y-axis symmetry. All right, let's try origin. So we're going to change x with minus x and y with minus y. So the x on the left becomes minus x, and the y inside becomes a minus y. The negative on the right gets absorbed by those absolute values, so it's going to disappear, but the negative on the left is going to stay put. And when I divide through by it to finish solving for x, I can just move that negative up to the top, just to clean it up a little bit and make it look nicer, and that is not going to give me back the original. So we do not have origin symmetry, so the only one that worked is x-axis symmetry. And that means this is reflected over that x-axis. So if I were to graph this, this would not be a function. It actually looks like a V on its side. So it doesn't pass that vertical line test. All right, let's try a couple more. Y equals 9 minus x squared. So let's find our intercepts. So to find the x-intercept, I'm going to let y be 0. So I'm going to put a 0 on this side of the equation. Now this one should be fairly simple to solve. I'm going to add that x squared over to the left side, take a square to both sides. Don't forget your plus or minus, because we do get two solutions. So if x is plus or minus 3, then the y value is 0. So I have two x-intercepts. To find the y-intercept, I'm going to let x be 0. So if I put a 0 in up here, that's going to go away, and I'll just get y equals 9. So 0, 9 will be my y-intercept. Now let's try our tests. So if I do x-axis symmetry, we're going to replace y with minus y. So the y on the left side gets swapped out with a minus y. Everything on the right side stays the same. I want to finish solving this for y so I can compare it to the original. So I'm going to divide through by a -1 everywhere. And that changes all my signs. So this becomes positive y equals -9 plus an x squared. And if I compare that to the original, it is not the same. So this does not work. Let's try y-axis symmetry. So I'm going to replace x with minus x. So the y doesn't get touched, it stays the same. And the x, using parentheses, gets replaced with a minus x. Now because that's an even power, the square is going to obliterate that negative inside of the parentheses. It's going to square away that negative. The minus that's out front from the subtraction stays put, but the negative inside the parentheses does get squared away. So this becomes a positive x squared, but because we were subtracting it from 9, that subtraction stays put. Is that the same as the original? Yes. So far we have y-axis symmetry. All right, let's try origin. So to get origin, we replace x with minus x and y with minus y. So the y on the left becomes minus y, and the x on the right, in parentheses, gets swapped out with a minus x. The negative on the left side stays put for now, and just as we said before, the minus on the inside gets squared away, but the subtraction will stay put. So this goes away and becomes a positive x squared, but we're subtracting it. To finish solving for y, divide through by a -1, which switches all my signs, so this becomes y equals -9 plus an x squared, which is not like my original, so that doesn't work. So I have y-axis symmetry, and that means it is an even function. And again, you could have predicted that because we had an x squared, which was an even power. Just because you think it might be even, you still need to show the test to show that it really does work. All right, one last example on this page. There's one more after that. All right, Let's try x to the fourth plus x equals y. Let's find our x-intercepts. So we're going to let y be 0. So a 0 goes on this side. And again, this is a higher power of x. It's x to the fourth. So to truly solve this correctly, the only way we're going to get lucky is if it factors. And it does because we can pull out an x, a GCF. And that's going to give me x equals 0. And if I set this factor to 0, subtract the 1 to the other side, undo the cube with the cube root of 1, or cube root of negative 1 stays negative 1. So when x is 0, y is 0, and when x is negative 1, y is 0. For the y-intercepts, I'm just going to let x be 0. So both of these x's become 0, and that means y is just 0. So again, the origin is both your x and your y-intercept. Alright, let's try our tests. So x-axis symmetry. Replace y with minus y. So the left-hand side with those x's stays the same, and the y on the right becomes a minus. To solve this for y, so I can compare it, I'm going to divide everything through by that negative, which makes all the terms on the left side become negative, so it's no longer going to look like the original, so this doesn't work. Let's try y-axis. So we're going to replace x with minus x using parentheses. So this is going to become parentheses negative x all raised to the fourth plus a negative x in parentheses, and I'm not touching the y. Now this negative is being raised to the fourth, which is an even power, so it's going to disappear. So this will become positive x to the fourth. This negative is being raised to an implied power of 1, which is odd, so it's going to stay there. So this is going to stay minus. Does that look like the original? No. So that doesn't work either. Alright, let's try the origin. So we replace x with minus x, y with minus y. So using parentheses on the left side, negative x to the fourth plus negative x equals negative y. I changed everything. So the fourth degree negative disappears. The first degree negative stays put, and the negative in front of the y stays put. To solve for y, divide through by a negative 1 everywhere. So this becomes a negative x to the fourth. Negative over negative becomes positive, and this stays positive y. Does that look like the original? Again, no, because we have that extra minus in front. So this does not have any symmetry at all, since none of our tests worked. Okay, one last example with all these questions involved again. Let's start with our x and y intercepts again. So for my x-intercept, I would let y be 0. So this is going to go to 0, and this is going to go to 0. So we get 0 equals to 1. All my variables disappeared because when I multiply those x's times 0, they go away. Does 0 equal to 1? No. So that means there are no x-intercepts because we get a false statement. Let's try it for the y-intercepts. So this time we're going to let the x go to 0 here and the x go to 0 here. So we're going to get 0 plus 0 again. Does that equal to 1? No. So we get no y-intercepts. So this one, because you get 0 equals 1 no matter which variable you substitute in 0 for, it has no intercepts at all. It never touches the x-axis, it never touches the y-axis. Let's look at symmetry. Let me see if I can erase some of my circles here. Okay, so if we have x-axis symmetry, then I'd want to replace y with minus y. So leave the x to the fourth the way it is, but using parentheses, replace that y with a minus y raised to the fourth. And then I'm going to replace the y over here with a minus y, and it would look like that. Now this negative, because it's to the fourth power, disappears. So it's just x to the fourth, y to the fourth. This minus, since it's to the first power, stays, and just to make it cleaner, I can actually move it out front and make this a subtraction. So we get x to the fourth, y to the fourth, minus xy. Does that look like the original? No. Okay, let's try y-axis symmetry. So I'm going to replace x with minus x using parentheses. So this x becomes minus x to the fourth, y to the fourth, plus minus x times y. This negative goes away because it's an even power. This negative just gets pulled out front, stays put, and that no longer looks like the original. Finally, for origin, we replace both with minuses. So negative x to the fourth and negative y to the fourth plus negative x and negative y equals to 1. Now both of these negatives, since they're being raised to an even power, go away. So this will become x to the fourth, y to the fourth positive. Over here, these negatives would stay, but we have two of them. A negative times a negative becomes positive. So we get plus xy equals 1, which is good news because that means it does give us back the original. So that means we do have origin symmetry, which makes this an odd function, which you probably wouldn't have predicted because we have both a mixture of even and odd powers. So it's not always possible to tell just based on the powers whether you're even or odd. You do need to do the physical check of the test to prove one way or the other. Okay? Another kind of question that I could ask you is, given a partial graph or a piece of a graph, complete it so that it has a certain type of symmetry. So what we're going to do, and let me draw in my axis here so it's a little bit more visible. There's your x-axis. We are going to complete these graphs so that they have x-axis, y-axis, and origin symmetry. So remember, if something has x-axis symmetry, that means you should be able to reflect it over that x-axis and get the image reflected over. So if this point is at a height of 3, when I reflect it over that x-axis, now it's going to be at negative 3. This point is at a height of 0. When I flip it over that x-axis, it doesn't move. This same shape needs to be reflected over. So if we have to start here and stop here and have that curved shape, then you can see that it would have to look something like that. And then this point is at about, let's see, 1, 2, 3, 4, 5, 5.5 for the x value, and 1, 2, 3 high. So it's going to go down 3 and be right about here when I reflect it over that x-axis. And between here and here I have a straight line, so between here and here I want to have a straight line as well. So that piece in red would be the reflection. So the whole graph completely is symmetric with respect to the x-axis. Okay, now let's try this again, but now we're going to reflect it over the y-axis. So if I take this point and I reflect it over that y-axis, it's not going to change at all. The x-axis, or the x-coordinate, stays 0 both ways. This point over here is at about 1, 2, 3. So when I reflect that over the y-axis, now it's going to be at negative 3. And between here and here I had that curve, so between these 2 points I want to maintain that curve. And then this point is at about 1, 2, 3, 4, 5, 6, and it's going to get reflected to negative 6. It gets reflected to its opposite. So it would be at right about here at a height of 3, and a straight line between these 2 points, so I want to maintain that straight line over here. So we get that mirror image across that y-axis. Okay, now for origin symmetry. Remember, origin symmetry swaps the x's and the y's. So if this point right here is at 0, 3, when I swap 0 with its opposite, that stays 0. And when I swap y with its opposite, it becomes negative 3. So this point is actually going to stay at 0 for x, but it's going to now be down at negative 3 for y. This point is at 1, 2, 3, 0. So I'm going to switch the x to its opposite, which makes it negative 3, and I'm going to switch its y to its opposite, but the opposite of 0 stays 0. So this becomes negative 3 comma 0. So that would be this dot right here. And then this point up here is at 1, 2, 3, 4, 5, 6, comma 3. So when I swap its x with its opposite, that becomes negative 6, and its y swapped becomes negative 3. So that would be this point right here. So those are those three main points, and now what we want to do is connect them in the appropriate shape. So between this point and this point we had a curve, and that was this point and this point, so we want to maintain that curve. And between these two I had that straight line, so between these two I want to have that straight line as well. So you can visualize this being rotated 180 degrees over that origin and getting the same image back. Okay, to finish up, we're just going to do a couple of circle problems for some extra review. This first one should be relatively straightforward. We want to find the equation of a circle that has a center of 1, negative 4 and a radius of 8. And this should be pretty straightforward if you remember what we talked about earlier with the equation of a circle having a certain standard form. And that was that formula x minus h quantity squared plus y minus k quantity squared equals the radius squared. So we already know what we want our h and our k to be, and we know what we want our radius r to be. So all we have to do is plug things into the right spot and we're done. Now remember that you want opposite signs. So if I want my center to have an x coordinate of 1, then I need to have an x minus 1 in parentheses. If I want my y coordinate to be negative 4, then I want to see a plus 4 in my parentheses. And if I want my radius to be 8, then I need 8 squared, or 64, on the right-hand side. So that's it. Pretty simple. There's my equation of my circle. Okay, to finish up, we want to find the equation of a circle that has endpoints of its diameter at negative 1, 5 and 2, negative 3. So let's just visualize this for a moment. Negative 1, 5 would be about here, and 2, negative 3 would be about here. And that's the diameter of our circle. So you can kind of visualize maybe what this circle would have to look like. And we want to come up with its equation. So if you remember our standard form, x minus h squared plus y minus k squared equals r squared. In order to know its equation, we need to know its center, which is h comma k, and we need to know its radius, which would be the square root of that constant. So let's start with our center. What's it going to take to find out the center if we know these two endpoints of the diameter? Where's the center got to be located? You can visualize it's going to be right around here somewhere. And what's that called when you're halfway between these two endpoints? It's called your midpoint. So the center is located at the midpoint between these two endpoints of our diameter. So it's at the midpoint of negative 1, 5 and 2, negative 3. So then the next question is, well, how do you find a midpoint? Well, a midpoint is just like an average. That's exactly what a midpoint is. So to find a midpoint, you take the two x values and you find their average. So the x values are negative 1 and 2. And to find an average in math, you add them up and divide by 2. So we're going to take negative 1 plus 2, we're going to add them up, and we're going to divide that by 2. Then we're going to do the same thing for the y's. The average of the y's would be the sum, so 5 plus negative 3 divided by 2. If we simplify that, negative 1 plus 2 is 1, so this is 1/2. 5 plus negative 3 is 2. 2 over 2 becomes 1. So now we know our center. That's going to become our h and our k. So the only other thing we need is our radius. How do you find your radius? What's the radius going to be if all we know are these endpoints of our diameter? Well, your radius is this distance from here to here, that length. Now there's a couple ways you could do this. Since we just found our center, we could directly find that distance by finding the distance between the center point and that endpoint. If you didn't find the center first, like we did, you could find the radius from these 2 points all the way from the end over here to going over here by finding that whole distance and cutting it in half, because the radius is 1/2 the diameter length. So let's just do it that way, since you don't necessarily have to know the center in order to find the radius. So to find the diameter distance, you're going to need to use the distance formula. So the distance formula between any 2 points, x1, y1, and x2, y2, is given by this formula. It comes from the Pythagorean theorem. The distance between this point and this point would be the difference in the x's squared plus the difference in the y's squared. So if we are using our two diameter endpoints, -1, 5, and 2, -3, we're going to take these two x's, and it doesn't matter which one you start with. I'm going to start with the 2, and I'm going to subtract from it the other one, which would be -1. So you actually get a double negative here. So this is going to become plus plus. Then I'm going to subtract the y. Since I started with the 2, just to be consistent, I'm going to start with the -3, and I'm going to subtract the other y, which was 5. So we get a double negative on this first one, so 2 plus 1 becomes 3 squared. And -3 minus 5 is a -8, and that needs to get squared. 3 squared is 9. -8 squared becomes positive 64. So 9 plus 64 is 73. And that means we have square root of 73 for our total distance between our two endpoints. And remember, that distance between the two endpoints on either side of the circle, that was our diameter. So how do we get the radius from that? Well, remember that radius is equal to 1/2 of the diameter. So this is going to be 1/2 times the square root of 73, or I like to write that as the square root of 73 over 2. And that's going to be our radius r. So now if we try to put everything together into the equation of our circle, we now know our radius, and up here was our center. So let's recall what the equation of our circle is in general. A circle is going to have as its equation x minus h quantity squared plus y minus k quantity squared equals the radius squared. And in this problem, our h is this 1/2. So we want x minus 1/2 quantity squared. Remember, what's inside the parentheses should have the opposite sign of what you want your center to be. We want positive 1/2, so I need to have a minus 1/2 inside my parentheses. And the same is going to go for the 1. So I'm going to have plus y minus 1 quantity squared. So I need a -1 in here because I want a positive 1 up here for my center. And then finally on the right side we want our r squared, and here was our r. So what do you get when you square this value? Well, when you square 73 in a square root, you're squaring a square root, and that just cancels out the radical. So this just becomes 73 on top, and 2 squared just becomes 4. So the radius squared becomes 73 over 4. And here's our final equation of our circle. All right, that concludes our video lecture on the review of graphing, intercepts, and symmetry. Good luck!